In this video, we're going to be taking a look at semi-log and log-log graphs and how they can be used to create a model for a given data set if you don't know what the relationship is between the dependent and independent variables in that data set. So first, let's quickly revise what we already know about a couple of different types of graphs. So firstly, think about a linear function or a linear graph. We know that a linear form is y equals ax plus b, or you might be more familiar with y equals mx plus c, but in this case a would be the gradient and b would be the y-intercept. And if we were to plot that on a set of axes, it would look like a nice straight line, just something like this. What about an exponential model or an exponential graph? We know that exponential functions have the form y equals a b to the power of x, or in other words, x, the independent variable, is the exponent. So if we were to graph this, it would have this sort of shape, a bit of a curve to it. And lastly, let's consider a power function which has the form y equals ax to the power of b. So power and exponential look quite similar, except these two terms are switched around. So in this case, we have the independent variable being raised to the power of some constant, whereas in the exponential model, we have a constant being raised to the power of x, which changes because that's our variable. But let's come back to our power function. If we were to draw this one, its general shape would be starting at 0, 0, something like this. So you can see that a linear plot looks, you can identify it straight away because it's a straight line, whereas exponential and power functions, if you weren't given the original equation, can be hard to differentiate because they have a very similar shape. So if you've been given an equation and you're going to graph it, we can tell straight away whether it's going to be linear, exponential, or power by looking to see if the equation matches one of these forms. But what if you've been given a data set and you would like to fit an equation to it? We need to work out what sort of form the equation would take, or what the appropriate model would be to use. So to do that, we can use semi-log and log-log graphs. So if you've been given a data set, or you have a set of x, y values in a table or given to you in a particular way, the first step to do this would be to sketch a rough plot of the data. So let's say you've been given a table of values. You would draw up a Cartesian plane and draw the coordinates you've been given onto it. So two things could happen. You could sketch the plot the coordinates rather, and end up with something that looks a bit like this, which you can see if you were to fit a line of best fit to that, it would be a linear model. That looks roughly linear to me. So that suggests there is a linear relationship between the points in the data set, and it would take the form y equals ax plus b. And if that's the case, that's nice and easy to find an equation for, because you just fit a line to it, find the gradient and the y-intercept, and there's your model. But in the problems that we're going to be working with, the data set given to you could be an exponential or power model, and you would need to find an equation to fit that data set. So what could happen instead is that you plot the points that have been given to you, and you get something that looks more like this, which just at a glance you can see isn't really linear, because if you were to draw a line through that, a straight line, it wouldn't necessarily fit the data that's been given to you. It looks more like it has a bit of a curve to it. So in this case, we could assume that it's probably either an exponential or a power model, but just by looking at it, it's hard to tell which one, because as we already said, they look kind of similar. So we can use semi-log or log-log graphs to determine whether it's exponential, taking the form y equals ab to the power of x, or whether it's power, taking the form y equals ax to the power of b. So as I said, if it's not linear, and it's got a bit of a curve to it, what we're going to do is draw a semi-log graph to determine whether it's exponential or whether it's power form. So semi-log graph is what we're going to have a look at how to do. There are a couple of steps involved in this. The first one is to go to your set of xy values that you've been given, and for each y value you're going to take a log of it, or in other words log to base 10 y. So that means you get your calculator, and for every y value, let's say the first one is 2, you would enter in your calculator log 2 and put a new y value here for log 10y. What you would then do is plot x, the original x values, versus log 10y, and see what happens. So back over to our axes, our x-axis would remain the same. It's increasing in a linear fashion, but our y-axis is going to be log 10y. So rather than being simply y and increasing in a linear fashion, it's increasing in a logarithmic fashion. Hence the name semi-log, because it's half log, half linear. So what you would do is plot x versus log 10y. When you did that, if you plotted those points and what now resulted was something that looks like a linear model, that would mean that your data set is exponential. So let's have a look at why that is the case. We're going to consider, as an example, the equation y equals 10 to the power of x. This is an exponential function, which I've graphed here in Desmos, and it looks like this, an exponential model. Okay, given the function y equals 10x, let's quickly draw a table of values. So I'm just going to use the values 0 to 5. And for each x value, I will plot a corresponding y value. So here we have 10 to the power of 0, which is 1, 10 to the power of 1, which is 10, 10 to the power of 2, which is 100, 10 to the power of 3, which is 1000, etc. 10,000, and finally 10 to the power of 5, 100,000. Okay, so as I said before, in order to do a semi-log graph, rather than working with our initial set of y values, we're going to create an additional column and call it log 10y, which means I'm going to take a log to base 10 of each of these y values. So by doing that, I'm going to get 0, 1, 2, 3, 4, 5. So in other words, by taking a log to base 10 of each of these y values, what we're finding is the number of times that 10 is being multiplied by itself to get to whatever that original y value was. So in other words, 10 to the power of 0 equals 1, 10 to the power of 1 equals 10, 10 to the power of 2 equals 100, etc. So by doing this, we can see that the log y values are now increasing in a linear fashion. Here they were increasing exponentially, being multiplied by 10 each time, but here they're just going up by a consistent gradient of 1. This shows us that in the original function, the exponent is increasing as the x values increase, which is the definition of an exponential function, where the x variable is the exponent. So therefore, we've proven that this set of data does in fact resemble an exponential model, which is why if you modeled an exponential function on a semi-log axis, you would get a linear model. Let's consider a very similar function, slightly different. Rather than y equals 10 to the power of x, let's consider y equals 2 to the power of x. So again, I'm just going to quickly draw up a table of values. So x I will let equal 0 through to 5. Y will be 2 to the power of 0, which is 1. Anything to the power of 0 is 1. 2 to the power of 1, which is 2. 2 to the power of 2, which is 4, etc. We're going to have 8, 16, and 32. Okay, once again, we're going to take a log to the base 10 of each of those y values in order to construct a semi-log graph. So that means in my calculator I put log 1 and I'll get 0, log 2 I'll get 0.3, log of 4 I will get 0.6, log of 8 I will get 0.9, log of 16 1.2, and log of 32 1.5. Rounding those off to just one decimal place to keep it nice and simple. Okay, firstly, don't be confused by these numbers which from a glance look quite unfamiliar because they don't seem to fit in with the model and the numbers we've already considered. It's not as neat as the last example we considered of y equals 10 to the power of x. This is because if we were using log to base 2, the results would be easier to understand because we'd get, once again, 0, 1, 2, 3, 4, 5. But our calculators only like it when we do log to base 10. So anytime we take log of the y values, it's going to be to base 10. So we'll always work with this base. So when we look at, for example, log of 4, and we got the result 0.6, that means that 10 to the power of 0.6 equals 4. So once again, if we look at these log y results, you can see by going from one to the next that they are actually increasing in a linear fashion. So it's going up by 0.3 each time. So 0 to 0.3, add another 0.3 to get 0.6, up to 0.9, etc. So again, we can see that these results are linear. They're increasing in a linear fashion with a gradient of 0.3. So if you were to plot x versus log 10y, that's x versus log 10y, on a semi-log axis, you would get a straight line. And so if you do this step, you take a log of your y values and you plot it on a semi-log axis and your result is linear, that means that the original function modeling your data set was an exponential function. On the other hand, if you take a log of your y values, you plot it, and it still doesn't look linear on the semi-log axes, or there is no consistent gradient between the y values, then we have to take it a step further and draw a log-log graph. Based on what you now know about semi-log graphs, you can probably make some guesses as to what a log-log graph could be. We know that semi-log meant that the x values remained the same, but the y values were taken logs of. So on a log-log graph, we take logs of both values. So down here we'd have log 10x, and along here log 10y. So both axes are logarithmic. So in order to take this a step further and do a log-log graph, that means that in your table of values, you would have to take logs of both the x values and the y values. So let's do that as an example. Let's consider the function y equals x squared, which is a power model, because it's your x variable to the power of something, which would be a constant. I'm going to construct a table of values, but in this case I need to add an additional column. So I'm going to have x log 10x, y, and log 10y. So first of all, let's go and do our original x, y values. So we're looking at y equals x squared, which is just your basic parabola. So if I let x equal 0, 1, 2, 3, 4, then my y values are going to be those values squared. So it would be 0, 1, 4, 9, and 16. Now, because we're doing a log-log graph, we need to go and take logs of each of the x values and then each of the y values. So first of all, log of 0 is invalid. There's no answer for that. Log of 1 is 0. Log of 2, 0.3. Log of 3, 0.48. And log of 4, 0.6. Okay, now I'm going to go and do the same thing again for the y values. So once again, log of 0, invalid. Log of 1 is 0. Log 4, 0.6. Log of 9, 0.95. And log of 16, 1.2. Okay, so in addition to the original xy values from our function y equals x squared, what we've also done is taken logs of the x values and taken logs of the y values, all to base 10. But what does this reveal? Well, in the power function y equals x squared, each x value is multiplied by itself once, or being raised to the power of 2. By taking logs of both the x values and the y values, and then examining the relationship between these log x values and the log y values, it reveals something about the relationship, reveals something about this relationship up here. So if we look at these coordinates, the x and the y coordinates, we can see that there is a bit of a relationship between them. You can see that log y is roughly double log x. Or in other words, log 10y is 2 times log 10x. What this tells us is that the exponent in our original power model was 2. So I'll say that again, log 10x is being multiplied by 2 in each case to get log 10y. That factor, 2, is the exponent in our original power model. So if you were to plot this on a log-log graph, it would be linear, taking the form y equals 2x, because in each case the log y value is double the x value. So just to revise that process quickly, if you're given a data set and you don't know what the relationship is, then you first of all plot it. If it looks linear, then that's easy. You just fit a linear model to it. If it still doesn't look linear, you draw a semi-log graph. If it then looks linear, you've got an exponential model. If it's still not linear, then you take it a step further to do a log-log graph. And then if it now looks linear on your log-log graph, then you have a power function. Okay, so you've found the correct model. Now what happens? Once you've selected the graph that most closely fits the straight line, we need to draw a line of best fit, which must be linear. So let's consider an example. Our exponential function up here, y equals 2 to the power of x. In this case, we knew what the original function was, but let's pretend that we didn't and we only had the data set. So let's pretend we didn't have this information. All we had was some x and some y values. We found from taking logs of the y values that x versus log of y produced a linear function with a gradient of 0.3. So we found out that y equals 0.3x in that line of best fit. To make this mean something in the context of the original data set, we need to convert it back to an exponential model. So to do that, we need to let y equal log of y. That's because we originally converted y to log of 10y. So now we need to reflect that in our equation. So I'm just going to take this back down here. So we have y equals 0.3x. Now this was the line of best fit that we found from analysing the gradient or the increase in those log y values. You could also draw it and actually fit a line manually to it, or you could do it digitally as well, which we'll have a look at later. But for now, let's just go with the fact that our line of best fit was roughly modelled by y equals 0.3x. Now I said we have to let y equal log 10y, and then write the rest of the equation as normal. And now we rearrange until we have something that fits an exponential model. So if log 10y equals 0.3x, then that means 10 to the power of 0.3x equals y. Okay, let's just break this left-hand side into two parts and say that 10 to the power of 0.3 to the power of x equals y. We can evaluate or simplify 10 to the power of 0.3, and what we end up with is roughly 2, or 2 to the power of x equals y, which is the model, the exponential model for the data set that we were given. Let's have a look now at our power example. So let's go back to our example of y equals x squared, our power model. Now again, in this case, we were actually given the model and we drew up a table of values, but let's just pretend that we weren't given this information. All we had was a table of x, y values, and we needed to determine the relationship between those values. So we found by taking log of x and log of y that the log y values will roughly double the log x values, which means that if we were to model that in a linear equation or fit a line of best fit to it, what you would end up with is y equals 2x, or in other words, these values, the y values, are double the x values. So this is a similar process here. Because we took a log of x and log of y values, in order to convert this back into a power function, we need to let y equal log 10y, log to base 10 of y, and we need to let x equal log to base 10 of x. So I'm going to scroll back down here and we're going to do that now. So y equals 2x. That's our line of best fit on the log-log graph. To convert it back into a power form, we're going to let y equal log 10y, and we're going to let x equal log 10 of x. Now, once again, we have to rearrange this equation to make y the subject to get it back into power form. So let's do that. I'll rewrite this step. Log 10 of y equals, using log definition, log to base 10 of x squared. 2 log to base 10 of x is the same as log to base 10 of x squared. Now I'm going to take this over to the left-hand side. Log to base 10 of y minus log to base 10 of x squared equals 0. Once again, using log definition, log to base 10 y divided by x squared equals 0. This means that 10 to the power of 0, which equals 1, equals y over x squared. Now all I want to do is isolate y, so to do that I multiply both sides by x squared, and what I end up with is y equals x squared. So now by doing that I found out that the power model that best fits the data set given to me is y equals x squared. Now this same process that I've done here to find a power model and here to find an exponential model will work for any other line of best fit that you have modelled either on a semi-log graph for exponential models or on a log-log graph for power models. And now what you have found is an exponential or power model that best fits the data set you've been given. We've done some simple examples here In my next video, we will look at a practical application of semi-log and log-log graphs to fit exponential and power models, and how you can use Excel or graphing calculators to assist you in creating your graphs and finding the most accurate line of best fit to produce your exponential or power model.